The transition to chiplet-based architectures has shifted the primary bottleneck of semiconductor manufacturing. Front-end lithography is no longer the sole constraint. The critical point of physical failure now lies in back-end substrate integration, specifically the supply of Ajinomoto buildup film. This ultra-thin epoxy resin dielectric is the global standard for high-density interconnect layers. The market deficit peaked in 2022 at 14.0%. Despite capital expenditure by the sole supplier, Ajinomoto Fine Techno, a structural deficit of 10.1% is projected for 2025. New film casting lines require 24 to 36 months to qualify and scale. Consequently, lead times for high-end substrates remain elevated at 30 to 40 weeks. This material concentration mirrors the 1999 JSR Corporation photoresist bottleneck, where a single chemical plant disruption stalled global chip production. Physical scaling of advanced integrated circuit packages compounds this raw material shortage. As package sizes grow from 35mm footprints to 75 and 100mm modules, substrate yield rates collapse. Larger surface areas increase the risk of substrate warpage and microvia misalignment during fabrication. Yields drop from 95.0% for standard packages to below 50.0% for 75mm designs. For next-generation AI accelerators measuring 100mm, yields plummet to 18.0%. This yield collapse drives an 11.5 times manufacturing cost multiplier. Furthermore, the required ABF layers scale from 4 to 16. This exponential increase in layer count raises the probability of a fatal dielectric defect, generating high scrap rates that worsen the underlying material deficit. The downstream processing of raw film into finished substrates is highly concentrated. Japanese fabricators Ibiden and Shinko Electric control a combined 60.0% of the high-end high-performance computing substrate market. This concentrates critical AI accelerator supply chains within Japanese jurisdiction. Taiwanese fabricators account for 41.0% of global capacity, exposing the supply chain to acute geopolitical risks in the Taiwan Strait. The high-end segment is significantly more consolidated than the general market. The top three players control 84.0% of advanced packaging substrate supply. This extreme corporate and geographic concentration creates a systemic single point of failure. Building more silicon foundries cannot bypass this intermediate processing bottleneck. Hafnium is a hostage byproduct of nuclear-grade zirconium refining. It occurs at a rigid natural ratio of 1 part hafnium to 50 parts zirconium. Because of this physical constraint, hafnium supply cannot scale independently to meet market demand. Global nuclear-grade zirconium production has remained highly inelastic, fluctuating between 3,600 and 4,250 metric tons annually over the past decade. Consequently, the hafnium supply curve is virtually vertical. This structural rigidity triggered a severe price divergence after 2021. Hafnium spot prices surged from $1,600 per kilogram in 2021 to $5,200 per kilogram in 2024. This represents a 225% increase, completely decoupled from zirconium production levels. The structural deficit in the global hafnium market emerged in 2021 and expanded to 21 metric tons by 2024. This deficit now represents approximately 20% of total global demand. To bridge this gap, aerospace manufacturers have aggressively drawn down private and state inventories. Cumulative strategic stockpile drawdowns exceeded 53 metric tons between 2021 and 2024. These buffer stocks are now largely exhausted. Refined hafnium supply growth is capped at less than 2% per year. This slow growth is dictated by the long capital expenditure cycles of nuclear-grade zirconium purification facilities. The aerospace sector faces a prolonged and unyielding supply bottleneck. Hafnium is metallurgically indispensable for high-pressure turbine blades in modern jet engines. Adding small fractions of the metal stabilizes nickel-based single-crystal superalloys at extreme temperatures. Reducing hafnium content from 0.15% in René N5 to 0.02% in experimental alloys reduces the turbine blade's oxidation life by 60%. Third-generation superalloys like René N6 require 0.02% to 0.20% hafnium to withstand operating temperatures of 1180 degrees Celsius. Eliminating hafnium entirely drops the maximum operating temperature by 70 degrees Celsius. This temperature drop directly degrades engine thermodynamic efficiency and increases fuel burn. Aerospace manufacturers cannot easily substitute this element without compromising commercial and military aviation performance. The commercialization of next-generation high-temperature gas-cooled reactors faces an immediate physical constraint. The rate-limiting step is not reactor construction, but the fabrication of tristructural isotropic, or TRISO, fuel. Cumulative fuel demand is projected to reach 150 metric tons of heavy metal by 2032. However, Western fabrication capacity, led by BWXT and X-Energy, will only reach 15 metric tons per year by that date. This mismatch creates a persistent structural deficit throughout the decade. A single 320 megawatt thermal reactor requires an initial core load of 15 metric tons. This single startup load consumes 100% of the entire projected Western fabrication capacity for 2032. The supply chain cannot support simultaneous multi-reactor deployments. The manufacturing bottleneck is rooted in the physics of fluidized bed chemical vapor deposition. Applying 4 distinct microscopic coatings to uranium kernels requires extreme thermal precision. The silicon carbide deposition stage operates at 1500 degrees Celsius using highly corrosive methyltrichlorosilane gas. This step has an individual yield of 89.0% due to single-digit micrometer tolerances. Cumulative material yield loss across all stages reaches 36.8%. Consequently, producing 1.0 kilogram of qualified TRISO fuel requires 1.58 kilograms of raw uranium feedstock. Furthermore, fluidization instabilities in the coating chambers limit batch sizes to just 5 to 10 kilograms. This physical limit prevents the economies of scale typical of conventional nuclear fuel fabrication. This fabrication bottleneck is compounded by an upstream feedstock monopoly. TRISO fuel requires high-assay low-enriched uranium, enriched to between 5 and 20%. Russia's Statone 10X controls over 95% of current global commercial supply. This creates an acute geopolitical vulnerability for Western reactor developers. Domestic United States capacity at Centrus Energy is limited to a demonstration cascade producing less than 1.0 metric ton per year. Scaling Western enrichment capacity to 21.0 metric tons by 2030 requires at least $2.5 billion in capital investment. Without this infrastructure, the transition to advanced gas-cooled reactors remains entirely dependent on foreign state-controlled monopolies. This vulnerability mirrors the early industrial scaling hurdles of the Manhattan Project. The synchronization of global navigation satellites, military communications, and financial networks depends on a single physical constant: the hyperfine transition frequency of the Cesium-133 atom. Yet the physical supply chain for this element is entirely monopolized. Only 3 operational mines globally produce pollucite, the primary mineral precursor for cesium. These deposits in Canada, Zimbabwe, and Australia are under the absolute corporate control of China's Sinomine Resource Group. The United States is 100% import-reliant on these critical minerals. Total global production is highly restricted, yielding less than 1,000 metric tons of pollucite equivalent per year. This geological bottleneck creates an absolute single point of failure for Western defense infrastructure. The vulnerability is not merely extractive, it is concentrated in the midstream refining process. Prior to 2019, Western entities controlled approximately 65% of intermediate chemical processing capacity. This changed when Sinomine Resource Group acquired Cabot Specialty Fluids for $135 million. This single transaction transferred 95% of global high-purity chemical conversion capacity to Chinese ownership. Today, purifying cesium to the 99.999% level required for atomic clocks occurs at just 3 sites. 2 are in mainland China, and the third is a Chinese-owned facility in Leverkusen, Germany. This consolidation mirrors the late 19th century British monopoly on natural rubber, which forced rival powers to accept severe strategic vulnerabilities. This processing monopoly directly threatens the production of high-precision timing systems. Demand for chip-scale atomic clocks has grown at an annual rate of 18.3% since 2018. These devices are critical for military electronic warfare protection and 5G network synchronization. In response to this demand and strategic stockpiling, 5N-grade cesium metal prices rose 210%. Prices escalated from $1,900 per kilogram in 2018 to $5,900 in 2024. Manufacturing these clocks is highly sensitive to precursor purity. Even part per million impurities of oxygen or moisture render the core physics package inoperable. Western defense systems remain tethered to a highly fragile, foreign-controlled chemical corridor. The physical infrastructure of the global internet depends on a highly consolidated chemical corridor. While Western nations draw optical fiber, they rely almost entirely on Chinese chemical purification. China's share of global optical-grade silicon tetrachloride refining capacity expanded from 52.5% in 2018 to 73.2% in 2024. This growth was driven by direct integration with massive domestic polysilicon hubs. Meanwhile, North American and European refining capacities contracted by 10.0% and 16.7%, respectively. This structural deficit leaves over 23,500 metric tons of annual Preform production vulnerable to unilateral export controls. Industrial-grade silicon tetrachloride from solar photovoltaic production is highly abundant, but it is unusable for telecommunications. The physical bottleneck lies in the elimination of transition metal impurities, specifically iron. To prevent signal degradation at key transmission windows, iron concentrations must be suppressed below 1.0 part per billion. An increase in precursor iron from 0.1 parts per billion to 5.0 parts per billion escalates attenuation at 1550 nanometers by 222%. This degradation renders the resulting optical fiber useless for long-haul networks. Achieving the 8 nines purity required to maintain signal integrity demands continuous, hermetic fractional distillation. The purification process is defined by steep energy requirements and compounding material losses. The final ultrapurification stage alone consumes 28.4 kilowatt-hours per kilogram of output. This single stage accounts for 50.0% of the total energy consumed across the entire distillation sequence. Furthermore, cumulative yield loss reaches 29.5% by the end of the process. Nearly one-third of the initial feedstock is discarded or downgraded. This high resource intensity drives a steep cost curve, forcing a premium of over 400% for optical-grade precursors relative to industrial-grade material. This economic barrier prevents rapid Western supply chain relocation. Stationary grid storage is transitioning to sodium-ion chemistry to bypass lithium resource constraints. However, this shift is fundamentally bottlenecked by the physical chemistry of the anode. Sodium ions are 34% larger than lithium ions, preventing them from intercalating into standard graphite. This physical limitation forces the use of specialized hard carbon. Global demand for hard carbon anodes is projected to expand from 1,500 metric tons in 2022 to 165,000 metric tons by 2030. This represents a compound annual growth rate of 79.8%. The resulting supply deficit will peak at 23.2% in 2025. This bottleneck is driven by the slow commissioning of high-temperature, inert atmosphere rotary kilns. Even by 2030, a persistent 12.1% structural deficit will remain due to precursor qualification delays. The hard carbon supply chain faces a fundamental material trilemma. Manufacturers must balance cost, electrochemical performance, and structural uniformity. Synthetic phenolic resins offer the highest performance, yielding 340 mAh per gram and a minimal 1.5% batch variance. However, synthetic resins carry a severe cost penalty of $6,800 per ton. Cheap biomass alternatives like coconut shells cost $1,800 per ton, but exhibit a high 14.5% batch-to-batch variance. This variance destabilizes cell matching in large-scale utility grid packs. Furthermore, low carbonization yields across all precursors compound the processing bottleneck. Yields range from 28 to 52%. This means up to 3.5 tons of raw precursor must be thermally processed to produce a single ton of battery-grade hard carbon. This yield loss mirrors Edward Aikeson's early struggles to commercialize synthetic graphite in the late 19th century. The chemical purity of the precursor directly dictates the macroeconomic viability of sodium-ion technology. First-cycle Coulombic efficiency is the primary determinant of cell-level energy density. A drop in this efficiency, from 85% to 70%, causes a 33% reduction in energy density. This performance collapse occurs because low-efficiency anodes irreversibly consume active sodium ions during the initial charge cycle. These lost ions are trapped in the solid electrolyte interphase layer, permanently reducing cell capacity. To compete with lithium iron phosphate grid storage, which delivers 160 to 180 watt-hours per kilogram, sodium-ion cells require an efficiency exceeding 85%. Achieving this threshold currently requires either expensive synthetic precursors or costly pre-sodiumation steps. The anode precursor bottleneck remains the primary barrier to scaling low-cost stationary storage. The physical dimensions of maritime corridors dictate the efficiency of global energy distribution. In the Houston Ship Channel, draft restrictions impose severe capacity and financial penalties on high-capacity tankers. At a restricted depth of 40 feet, very large crude carriers must light load by up to 35.0% of their deadweight tonnage. This underkeel safety margin prevents optimal asset utilization. Daily demurrage costs for delayed tankers scale nonlinearly, averaging $65,000 per vessel when draft limits block high-tide transits. Deepening the channel to 46 feet under Project 11 increases Suezmax utilization to 100.0%. This structural adjustment reduces average demurrage costs by 69.2%, down to $20,000 per day. Expanding channel capacity introduces a secondary physical bottleneck, the disposal of dredged sediment. Deepening 45 miles of waterway requires vast, isolated containment basins. Cumulative sediment extraction is projected to reach 138.5 million cubic yards by 2026. This rapid accumulation has depleted active dredged material placement areas. Remaining disposal capacity has collapsed from 85.0 million cubic yards in 2018 to just 1.2 million cubic yards. This structural deficit in containment volume forces a 40.0% increase in capital expenditure. Operators must acquire expensive upland sites and raise existing dikes to prevent a complete suspension of dredging operations. The mismatch between landside petrochemical expansion and marine infrastructure limits macroeconomic growth. U.S. Gulf Coast petrochemical export volumes rose 100.0% between 2016 and 2024, reaching 84.2 million metric tons. However, the narrow channel prevents two-way transit for wide-body vessels. This physical constraint has driven average transit delays from 11.5 hours to 29.5 hours. This divergence acts as a systemic drag on the export efficiency of liquefied petroleum gas and polymers. Localized bathymetric constraints remain the ultimate arbiter of global trade throughput. This dynamic mirrors the mid-20th century deepening of the Suez Canal, where physical geography forced a structural redesign of global shipping logistics. The physical limits of planar lithography forced solid-state storage into three-dimensional architectures. In 3D NAND, memory cells are stacked vertically, requiring deep channel etches filled with tungsten metal to form word lines. This metallization process relies on the chemical vapor deposition of tungsten hexafluoride. As layer counts scale from 128 to 232, tungsten hexafluoride consumption per wafer increases by approximately 45%. Global demand for electronic-grade gas is projected to scale from 4,100 metric tons in 2022 to over 7,300 metric tons by 2028. This represents a compound annual growth rate of 10.1%. At 300-plus layers, vertical aspect ratios exceed 100 to 1. These extreme geometries require extended deposition times. The resulting process inefficiency increases the gas-to-solid waste ratio, compounding volumetric demand. While raw tungsten ore is abundant, the capacity to purify it to electronic-grade standards is highly consolidated. The top three manufacturers control 78% of global purification capacity for 5N5 purity tungsten hexafluoride. These firms are South Korea's SK Materials, Japan's Kanto Denka, and the United States-based Merck. South Korea and Japan combined control 71% of global high-purity synthesis capacity. This concentrates the midstream supply chain within the East Asian Semiconductor Corridor. Chinese domestic capacity, led by the Liming Research Institute, is expanding rapidly to support domestic fabs like YMTC. However, export controls and strict qualification barriers prevent this capacity from easing Western supply constraints. The high-purity chemical corridor remains an effective oligopoly. The transition from raw ore to electronic-grade gas involves compounding material losses and extreme chemical hazards. The cumulative material yield from raw tungsten, concentrate to packaged gas, is approximately 50%. Half of the starting tungsten is lost or recycled during processing. Direct fluorination of tungsten powder requires highly corrosive elemental fluorine gas generated on-site. This step introduces severe operational hazards and localized supply constraints. The final fractional distillation step is the most capital and energy-intensive phase. It suffers a 25% yield loss to eliminate transition metal impurities down to subpart per billion levels. This extreme purification is necessary to prevent resistance spikes and gate oxide breakdown in 3D NAND devices.